So, hello everyone, we are back. What we are studying in the previous class, how to apply Boltzmann plot technique for measurement of plasma temperature. So, we are explaining that using the setup of spectrometer, fiber and the analyzing software, we can record intensity of the emission spectra at different wavelengths, and the spectral signature is basically signature of specific species which are present in the plasma. Now, depending on the level population, the transition happens from certain level to certain level, and that emission is getting recorded by the spectrometer. So, the energy levels are very specific for very specific atoms. Like hydrogen atom, you have all read the energy levels where they will be, they are precisely determined. Okay. The same is true for every atoms. Now, that you may get emission not only from the atomic transition, also from the molecular transitions. So, rotational and vibrational spectra of the molecules you can also get recorded in such spectrum that we will be showing you in some slides in the later lectures. But for the time being, if you are getting some emission spectra like this, how to determine the plasma temperature from that? So, let me first explain you the basic principle behind this. You know that according to Boltzmann distribution, the number of electrons at certain say higher energy state is proportional to exponents of minus E by kT, where E is the energy level. Okay. Now, at a certain temperature, this is the population of the energy level E, and the transition of the electrons from that level to the other level which are allowed depends on the population of that level. More the population, more will be the intensity. Okay. So, the intensity of the line what you are getting is proportional to the number of electrons that are in that level from which the transition is taking place, and intensity is proportional to number density, and number density proportional to exponential factor E of that energy level by kT. Now, if you take log of that intensity, then it is becoming proportional to the energy level itself, and you see that the exponential factor is including exponential, the argument in the exponent is having a term of the form E by kT. So, now when you are taking log, that is proportional to E by kT, and if you now plot intensity as a function of energy, then the relationship is linear and the slope is 1 by kT. So, just finding the slope you can find the temperature. So, this is the at the very basic things, but there are many other factors which influence the ultimate intensity that you are getting. So, what are they? They are the influencing factors are transition probability, the degeneracy of the level. Okay. So, they are the other primary influencing factors. So, finally, if you take the accurate expression of the intensity as a function of the energy of the upper energy level where from the transition is taking place, then what you get, the exact expression looks like this. So, certain temperature T, the level population is such that the intensity of the transition from U to I U is the upper level and I is the level where you are getting the transition, that ith line. So this is the wavelength lambda ui. Then this Gu is the degeneration of the upper level and AUI is the transition probability of that level. Okay. And then from that level, then EU is the upper energy level and T is the temperature, and as you know there will be some constant C which is absorbing rest of the parameters. So finally, if you are able to note the intensity of the line, then you are able to get a relationship of this kind which relates the intensity with the upper energy level. Now you see that each of these transition corresponds to different energy levels. Okay. Not necessarily that the energy levels that you are considering EU, they will be different. They may be different, there is a high possibility that they will be different, but it may happen that from the same energy level, transitions are going on to multiple levels. So, say transition to one level is giving you one intensity, and the transition to the other level from the same upper energy level is giving you the another intensity. So, their wavelengths will be of course different, but the energy upper energy level may be the same. So, this may happen, what I am telling you, but in many cases actually many of these wavelengths what you are seeing, rather most of the wavelengths you will be finding that the upper energy levels are different. So, suppose I take this third number line which is you indexed as 3. For this line we note the intensity and we note the upper energy level. Okay. So, I get one this kind, then I take some other energy level, other wavelength here, say 7 number, and for that I get another U and I get another intensity, and the rest of the parameters which are required are the wavelength. Of course, we know the wavelength by the spectrometer itself, because it has given me what is the wavelength of this 7th indexed this transition. Okay. Now, corresponding to these transitions, the energy level EU is known, because the energy levels of most of the atoms are now known to people, and they are available in database, wherefrom you can get that for this wavelength what are the upper energy level and what are the lower energy level. Then you know the intensity, from the spectrometer itself, you know the wavelength, and this G you get from the database, this A also you get from the database, then EU also get from the database. So what you are left with, you are having this complete equation. Okay. Now, rather than plotting this as getting the temperature from a single expression, you can make a plot y equal to mx plus c kind of equation you are getting, where m is 1 by kt and x is u. So x you vary over a wide range. What are the possible values over here for different wavelengths, and you know this y, this quantity is dependent on the intensity that you have measured using your spectrometer, and you know this C1 is not defined. So we should find a way to eliminate this effect of C1, and we can find a slope like y equal to mx, and from that slope we can find the 1 by kt value, and therefore we can get the temperature. So you now know that for every transition line this equation can be set, and the parameters that you require you can get from the database. So I have just now plotted all the 16 lines that you have marked over here, their necessary parameters. For example, the first line, this is at 696.5 nanometer. So this is the first one, 695.6 nanometer. Then you see that the sixth number, for example, it is near 760. So I get it that it is 763 exact value, and you see the upper energy level corresponds to this one, and degeneracy value for 7th one is 3, and the transition probability I get is this thing. So these values EU, GU and AUI I got from the database, and that database lists all these parameters as a function of the transition wavelength. So when you are getting to this 763.5 nanometer transition, that wavelength, they correspond to the upper energy level this one, degeneracy this one, and transition poverty this one. So where from we get this thing? We get this from the database that is already available in literature for most of the atoms, if not all. Okay. So wherever you are addressing some plasma, whenever you are addressing, you just go to the database and find out what are the wavelengths that are possible in the range where you are recording, and you will see that exactly those wavelengths are appearing in the spectrometer, what are listed over there. So you can precisely find out all these parameters as you are looking for. Now once you do that thing, I have just plotted that the same expression what you have seen over here, I lambda by GU log of and then EU, and what we get there, you see that E is the EU energy level and this is the logarithmic part, what is Y, and what you are seeing that the points, the plot as we have obtained from the intensity from the spectrometer, they are going like this. Okay. The thing is that you have noted that all of them are more or less falling on a straight line. And what is the slope of the straight line? That is 1 by kBt. So kV is the Boltzmann constant, you know. So once you know the slope, you can find out the temperature. Now in this, one interesting thing is that many of the time you will find that not all the wavelengths are falling on the straight line. So why they are not, all of them are not falling on the straight line? That is because the system is not in local thermal equilibrium. So whichever not in LTE, they will not fall in this curve. So you have already idea from our previous class that how the PLT occurs, that partial local thermodynamic equilibrium. And this kind of plasma, many of the times they are not in LTE but they are in PLT. So that the upper lying energy levels, they are populated as per the Boltzmann distribution but not the very lower lying energy levels. Okay. So whenever any transition is involving some lower lying energy levels, they may not exhibit the kind of equilibrium that you are looking for, because the system is not exactly in LTE for those lower lying energy levels, not in equilibrium. So those transitions may not fall in the straight line that you are plotting over here. Okay. So for example, this 12th transition line. So what was that? This is the 12th one. It is showing a appreciable intensity, although then what you are seeing that transition involves energy level, upper energy level, which is quite low in energy here, and possibly that is not populated as per the equilibrium distribution, Boltzmann distribution. So that is why it is not following this thing. But anyway, you are not bothered much about that, because you are going to find an average temperature. So why average temperature? Because if you had taken only one point, you see that it may go over here, it may come over here like that, and it may deviate from this. But when you are considering all the wavelengths, then from the slope of the line, when you are determining the temperature, then that is averaged over all the measurements that you have taken. So this is a pretty reliable temperature what you are getting. And when the scatter is much less, then you may be sure that the temperature that you are determining is quite accurate. Now the case of large volume, whatever I have told you, so whenever you are measuring, say, the temperature of an arc, they are very thin plasma and there is a very sharp temperature gradient, and for that the axial temperature measurement, this method is very accurate. But when you are going for, say, radio frequency plasma that we have discussed in our previous class, which is having a quite large diameter, So what is happening, when you are putting your fiber at certain location, you are trying to access the intensity that is emitted from the plasma along the cord. Then what is happening, whatever the atoms there at the core or at the periphery, they are radiating all together, and their intensity is coming and contributing to the intensity what your fiber is recording. So the problem here is that earlier in the case of arc, the central region temperature was so high that the outside temperature was so low that main contribution in the intensity was primarily coming from the central zone. But now what is happening, because it is a large volume plasma, so the intensity is coming from the center as well as from the middle of the your jet, I mean the middle of the radius actually. So and around, all of them are contributing significantly to the intensity that you are recording. So I am just trying to show you that over here. See, this is one radio frequency plasma. Okay, and this is the plasma that you are having over here. And as I have told you, the measurement technique, this is the optical bench, and this is 2f, this is 2f. An inverted image of this is formed over here, and here you have put a series of fiber. You see that there are many fibers are put on this range, and over which this image is formed, and simultaneously all these fibers are collecting the intensity. Okay. Now the intensity what you are collecting at different points from the center, suppose. So this is covering the whole diameter, and from along the diameter whatever atoms are there, they are radiating, and you are collecting the intensity corresponding to all the atoms which are in the line of sight along the diameter. All of them are contributing and recording the intensity. But here, which is there near the edge, they are intercepting less length of the plasma plume, because they are along the cord, okay, not along the diameter. So that their contribution which is coming from the lesser region, okay. But the ultimately what you are doing essentially, you are integrating the intensity along the line of sight, and that you are recording as intensity through your fiber in the spectrometer. Now here I am showing you one thing. This is the actual photograph. Okay. So the dots what you are seeing over here, they are basically in the CCD as it has appeared, and these dots are basically the light collected by different fibers that are here. So these fibers are collecting light. So this one is collecting whatever the atoms they are emitting along this cord, that is getting collected over here. As I was telling, the central one is collecting along the diameter, and they are coming over the here. Now, what we are interested in, that the radial distribution of temperature. So I want to know exactly what temperature is here, what temperature is at the center, what temperature is there near the periphery, but I am just helpless, because here all the atoms which are there along the cord, they all are radiating, and my fiber is capturing the intensity which is integrated over the whole length of line of sight. So I am here unable to identify exactly what is contribution from the center or what is contribution from the atoms which are there near the middle of the radius here. But the mathematicians are always there to give us a clue. So how to circumvent this problem? So for a given slice of plasma column, the emissivity of the plasma varies with radial distance as temperature varies. Okay. Now intensity received by a fiber positioned at the image plane is actually the integrated intensity over the line of sight, as I told you. Okay. Now the intensity received by a fiber at a distance y from the center can be expressed in terms of the radially varying local emission coefficient epsilon r. So this local emission coefficient, this is our interest. What is the emission that is coming out from a particular location, R location. That is our interest. We are not interested in the net intensity what we are getting. Okay. So how to find out that, and that is where mathematicians are helping us. Now what intensity you are getting is this is the expression. Now you should relate it with the actual geometry. So this is the y, this distance from the radius center you are collecting the light from here, and this is the r, the radius of the plasma column, and this is any arbitrary point r, where basically we want to know the what is the emission from there. Now based on this, actually this is the distance x what we are talking about. The intensity is I equal to at say distance y. So what you are getting at different y, I am collecting the intensities. So this one is y equal to 0 and this one is y equal to y. So like that actually. So I am collecting at different y. This is the y, and what I am getting the intensity, it is integrated at all r whatever you are getting, and then r square minus y square. So this integration you need to do, and r range from y to r, the capital r actually. So if you come over here, y is ranging from y to, this r is ranging from y to r. So what is this y? This r is ranging from when it is at this location, this is y, and when at this location is r is equal to r. At this location r is equal to y, and at this location r is equal to r. So you are integrating this from y to r, and you are multiplying by 2 because this side is also contributing to that. So this is what you are getting from as the total intensity what you are recording. Now what you are interested in? You are interested in finding out the radiation from that is coming from a particular location. This intensity you are interested in. But for the time being we are unable to do that. We are getting the total intensity. This integral can be inverted to find out the epsilon r through this inversion, and this inversion is called Abel inversion. Okay. So this technique of inverting this integral and getting the value of ER extracted from this, where you are getting the integrated intensity, is like this. So this I dash is the local spatial derivative of I. Okay. So this is the local derivative of I, and we will be able to find out that experimental data first fitted with appropriate function to find the derivative, this derivative, and then epsilon r is determined by this numerical integration. So we come over here. So this is the this radial distance, and emissivity what we extract from the integral after recording the intensity, this one IY, and this ER is obtained. This goes like this. Okay. And when you know the emissivity of particular radius, from that you can use the Boltzmann plot technique and you can find out the temperature. So Abel inversion essentially tells you that when there is a thick plasma and you are collecting the integrated intensity and you are interested in knowing what is the radiation from particular radial location, then you need to invert that integral and you find out the emission from particular radial distances, and from that you determine the temperature. So this is the temperature what we are getting, and this solid curve and the dotted curve, they basically is a validation that we are doing the correct Abel inversion. So the solid curve what you are getting is from our from this integral, and this data was for validation with respect to certain, you know, already reported values. So this is just to build the confidence that what we are doing is correct, and this kind of check is always required when you are actually going for practical application, so that you are confident that you are right in doing the calculations. So this is the kind of temperature we get along the radial distance, and you know these different acquisitions. The plasma, as you have seen, is quite unstable, this arc kind of thing, and because of the inherent instabilities, there are local variation in the emissivity as well as in the temperature. And what you are seeing that this is of course they are getting reflected in the measured temperature, but here what you are getting, the variation is quite less. You see the spread. Okay. Now, there are certain cases where you can find out accurate central axis temperature without doing Abel inversion. So, that technique I will tell you a little bit, because this is very much useful in case of arc kind of system which are being employed, you know, deployed in many practical applications. So, I am just showing you here one method where you can find out the temperature accurately without actually doing the Abel inversion techniques. In this case, a modified Boltzmann plot technique exists which can determine the central axis temperature, and here the relationship, earlier it was I lambda by Ga, instead this EU, the upper energy level, get multiplied over here, and you make a plot of this kind. So this is applicable in case of, you know, spatially unstable arc discharges, pulsating arcs as well. So this is a very useful thing when you are interested only in finding the central axis temperature. You can use this formula and you can make the same plot. You will get a linear plot, and from that plot you can find out the temperature. The limitation of this method is that especially for the central axis temperature, that this method can give you only the central axis temperature, axial temperature. It cannot give the radial profile. So when you are interested in finding a radial profile of the temperature distribution in a plasma, there is no other way except going for Abel inversion. So the technique that I have just described you need to capture the radiation from along the diameter, along the length of along the diameter of the plasma like this. So you get along different chords the intensity recorded, and from that intensity, if you do the Abel inversion, then you get the emissivity, and from that emissivity you can find out the radial distribution of temperature. And what I conclude by saying that if you are interested only in the axial distribution of temperature, in that case there a modified Boltzmann plot technique exists, where which is suitable even for bit unstable discharges, and you know the discharges which are having you know bit of instabilities in that, then also this works. And without Abel inversion, this doing this thing makes the method much simpler. So you can use this when you are interested only in the axial temperature distribution. So with this I stop, and I will discuss in the next class how you can find out the number density in the plasma from the emission spectra. So after that actually I will be going for this you know cold plasma systems, where you will be able to know that their invasive probes are very much possible because of the lower temperature of the gas. So you can use Langmuir probe, which you might have heard. They are widely used in diagnosis of the cold plasmas. I will tell you the issues with them as well, and different parameters that you can find out about the cold plasma using Langmuir probe. Okay, I stop here. See you in the next class.